Ladies and gentlemen, good morning, good afternoon, or good evening, wherever you are. My name is Rafal Zaleski, and I will lead this presentation for you today about the practical experience with SFRA technique. I hope you will enjoy it, and I hope it will be interesting for you to see what I'm going to present. Okay, so the presentation is organized by Altanova Group. Altanova is a company founded in past, currently in ESCO Group. It's so-called Doble company. And before I start, I would like to briefly introduce you to Altanova and basically to us, so that you know who we are, why we think we have experience, and what we can offer to you. So Altanova Group started from basically two companies which were founded in past. One was ISA, Instrumentazioni Sistemi Automatici, Italian company, founded in 1938, and another one was TechImp, founded in 1999. So ISA has been designing and manufacturing portable devices for electrical assets testing for more than 8 years. ISA advanced testing equipment is designed to perform tests on protective relays, power transformers, instrument transformers, circuit breakers, batteries, and many other high and medium voltage systems. TechImp, on the other side, is the major player in condition assessment and permanent monitoring of partial discharge activities in electrical assets. It is located in Bologna, in Italy, and develops, manufactures, and distributes products and systems and provides services for several applications like quality control, commissioning, tests, online, offline measurements, and permanent monitoring. So these two, they merge together to create Altanova Group in 2017, and then Inteliso joined Altanova Group in 2019. Inteliso offers wireless, passive, robust, real-time technology to continuously monitor the health of critical medium and low voltage electrical assets such as switchgears, cables, machines, generators, and ISO phase bars with electrically isolated and passive sensors. So you can see they complemented nicely the rest of the group. So this is how they all work together when ESCO welcomed them on board. ESCO is a big conglomerate of companies, including Doble. They all specialize in technologies, and Doble put an umbrella over the Altanova, so we are all now one big family. Who is Doble? I hope you all know that. Doble is a company with more than 100 years of experience. It was founded in 1920 by Frank Doble, and then continuously developed itself and technologies used in power industry with such milestones like M4000 instruments developed in 1993, which you probably know if you do have something to do with transformers. Then Doble was also taken on board by ESCO in 2007, since when it started, so continued fast, rapid developments, preparing or developing industry for future needs. Over the recent years, we also overtook, we acquired several big companies well known in the markets like Morgan Schaffer, Vanguard Instruments, Manta, Altanova, or Phoenix. So we are well known worldwide. We have as Altanova only, we are present in 100 countries. We have 12 global facility locations. We employ more than 150 employees, and we have more than 150 sales partners. And we have more than 5,000 customers globally. So briefly, our solutions, they focus on electrical test equipment, professional services, and monitoring systems. So actually, whatever you need for your assets, for electrical assets, I'm pretty sure we can offer something for you. So please contact us if you have any needs. Just to briefly list down Altanova testing and monitoring solutions. We can tell we are prepared for power transformers, circuit breakers, high voltage gas insulated switch gears, medium high voltage, extra high voltage cables, medium low voltage switch gears, batteries, current and voltage transformers, protective relays, meters and transducers, rotating machines, variable speed drives, and overhead lines. So I hope you got a little bit of information from that, but I also hope you already knew that. Now I'd like to come to this main subject of the presentation, which is SFRA technique. I decided to talk about the most practical aspect of it. So I will not introduce you to, let's say, R&D background of it or to some academic studies. What I wanted to show is a practical approach so that someone who wants to make a test knows how to do it, and he knows how to take most of appropriate and potentially available reference that might be possible to get. So as a word of introduction, I will just briefly say what the sweep frequency response analysis is, a so-called SFRA. So this is a test technique in which we apply variable frequency voltage to the coils of the transformers, and we scan the coils at the same time recording response of this coil. So basically we do it for each winding, each phase of a transformer, and by doing that we obtain results like the ones presented in a graph on the screen. You can see 3 lines which go along frequency range, and they have some damping parameters at different frequencies showing response of the winding. That response is equivalent of RLC network made by the winding, and therefore it is also a response of geometry of the winding. So if something happens to the transformer and windings get deformed, these responses are expected to change their shape as well. So this is comparative test. We always have to compare it with something. We can only tell the transformer is good if the trace is good. I will describe that further in details in a minute. But what does actually good response mean? That means it is as was expected. So we have several methods to assess whether it is as expected or not, and basically we do it by comparison. Here on the screen, the easiest way to compare by comparing 3 phases. When transformer is available for testing, 3 phases are normally all 3 available, and we can test all of them and compare. It's not always easy to interpret these results, but it's the easiest way to get. There are some other options. I will talk about them later. When we do it, when we suspect something happens to the transformer, we expect it could have deformed, but in order to have reference results, we should also do it. We recommend doing it as a routine test on transformer when it is on site, or at least if not routine, once in a lifetime after installation on site. It is also often made as a factory fingerprints in factory during FAT tests. It can be done before and after short circuit test, or before and after relocation. So whenever we expect something could have happened to geometry of the windings, it's good to do it, and it's good to have good reference from past, so it could be planned prior any happening to carry this out. There is plenty of papers on the internet. Many people got involved in this technique, writing papers, documents of different types. You can explore them indefinitely. There are 4 internationally renowned documents which I would like to guide you to, so that after this presentation, if you want to look for some more information, you can also look into these documents. There are 2 SFRA brochures, one from 2008 and one from 2020, 12 years apart. So the second one shows further development of interpretation of the results. It also looks at different indices that were present in the literature. So we reviewed these indices and we assessed them to check how effective they are, how sensitive to different types of fault. And the first one is maybe less focused on interpretation, but it's got more about the test technique. So as it was actually made in time when the technique was emerging and new products were developed. So this brochure was developed. There are 2 others. There's IEEE Guide for the Application of Interpretation and International Standards. They both describe how the test should be done, and they describe it in slightly different manners. So if you want to follow one up in your testing, you must be aware that there are different ideas presented in 2 different documents. Okay, so I would like to now talk about influencing factors. Influencing factors are factors which will make changes to your references, to changes to your traces if these factors are present. So you need to be careful how you test the transformer, and you need to be aware of these factors so that when you test the transformer, you exactly know in what condition it was tested, and especially if you compare with previous results or reference results, you have to know how the reference transformer was tested in order to reproduce the same test conditions. So the first factor I would like to mention is effect of core magnetization. If you do the tests during a test schedule, including, for example, winding resistance, you might notice that the trace will be different before and after winding magnetization, winding resistance measurement, because it magnetizes the core. And here we have example of such result. We have one trace measured, shifted to the lower frequency, another to the higher frequency range, but the difference is focused on low frequency range. So this is what you can expect if your core is magnetized. It's fortunately easy to identify, and if you have such results, you can investigate further, remagnetize the core, try again, and see what you are really looking at. Another obvious effect that can be seen in SFRA responses is tap position. If you look at your trace measured at 2 different tap positions, you would normally see differences in medium frequency range. So that's when you measure your transformer and you don't get good response, good comparison with reference results in this region, maybe you should think about tap position. Maybe you have wrong tap position during the test, or the reference was measured different tap position, and therefore your test is not matching the reference, and this is why you have difficulty in interpretation. When we talk about tap position, there must be one special case noted. If you consider the transformer with changeover selector, we have 2 pieces of 2 different rating plates. On one, we can see changeover selector, which selects direction in which the tap changer contacts are swept, or tap winding is actually approached. Then position of this changeover selector is also important, and this can be mistaken when you measure tap change transformer on nominal tap position. Nominal, I mean actually the middle tap position when changeover selector switches from one position to another. It switches after nominal tap position. So when it goes from bottom tap position, from lowest tap to highest tap, it will switch after that tap, and vice versa when it's going from top tap to the bottom tap, again after that tap, but this is when you test the tap transformer in nominal tap position. And if you approach it from one side or another, you will have different changeover selector position. And when you then measure the traces, you can notice quite a big differences between the measurements. So this is quite often my idea to interpret when I get results from someone else who did the test, and they made tests on first, middle, and top position, and last top position on phase A, and then they moved to phase B. They did the same but in opposite direction, and then again phase U from bottom tap to top tap, and then middle tap position for phase B difference. That's quite obvious interpretation that this could have happened, and you need to be aware of this. Tap changer located on high voltage side can also affect traces of low voltage side, even if it's not in the same circuit. There are apparently couplings that make it visible, and this is a number of tests which I did once to confirm it. So this is LV trace measured on the same coil several times on the same day, same conditions, but with different tap positions. Tap changer was located on high voltage side. This is low voltage winding, and we can see like when the traces change from one position to another position as tap changer was changing. And also that changeover selector made additional changes here. This is the green line when tap 13 was one tap after the nominal tap position. As you see, 12 was nominal. So you need to be aware of this as well. Another effect of state of the winding of the other winding of the transformer. Here is example of a transformer which has high voltage winding configurable. So it can be either set in 120 kilovolts connection, meaning two half coils are connected in series, or if they are connected in parallel, high voltage winding will have 60 kilovolts. So obviously they are mechanically in the same position, but there is a switch allowing that. And depending on which position that switch is in, low voltage winding again gives us different measurements. So when you have such a transformer, you have to make sure you test it on this tap position or this switch position which you want it to be tested. If you have reference, you need to look at which position it was tested before. And in your report, you need to describe how you tested. It is always important to write in your report something about the test setup, so that someone who comes some years later can reinstate the same test setup. Here another situation of effect of another winding. This was generator transformer with LV delta winding brought to the tank in 6 connections. So each coil was brought to tank separately, and the delta was constructed outside the transformer on site. When I tested this transformer, I had that delta completely disconnected, so there was no delta connection, and I just restored the delta by using jumping leads, shorting leads. So here we have two responses, one with delta closed and one with delta opened, as measured on high voltage side, which was not the one which was opened or closed. So again, condition of additional winding plays a role. Here another example of additional winding which can play a role. This was small transformer connected star delta, but delta was buried inside the transformer and grounded in one point, and it was not brought to tank. So for the first view, you wouldn't see terminals of that tertiary winding, and you wouldn't even know it is there until you looked at the rating plate. And our experience shows that when there is internally grounded tertiary winding in one corner, it quite often makes a mess with the traces measured on the other two coils, normally higher on the coils which are closer to the tertiary windings on the columns. So this is what we measured this time as well, and this is what you should be aware of. And I once made a simulation of this effect on another transformer. This one was in Ireland. I had a free winding transformer, which again, tertiary winding was was grounded in one corner. But this time, that corner was brought to tank. So we had two bushings, normally in service, closed to close the delta and grounded to this point here. I removed that connection and I simulated three conditions: one with completely open delta, one with delta closed but not earthed, and one with delta closed and earthed. And here you can see responses on another winding which are completely different. So condition of the other coils, the other windings, plays role again. Another influencing factor is an oil. It can happen that your transformer is drained from oil, and when that's the case, you can expect a horizontal shift between the lines. Here we can see one with the traces shifted to the left, the lower frequency range. This one is with oil, and without oil, it shifts towards higher frequencies. This is because permittivity of the oil and of the air is different, and this reflects our this is reflected by our traces, which are built on RLC network, the winding. Here in this example, we also had effect of high voltage bushings, which were missing during the second test without oil. Instead of that, we had small bushings as seen here on this picture. This was the history is that this was brand new transformer, which was first tested with oil during FAT tests, and then without oil in transportation condition. So that means oil was drained, and these bushings were replaced with small bushings connected to the windings just for purpose of this test. This is more and more often made in the industry. This technique is used to assess transportation. So for transportation, for transfer with 400 kV bushings, we cannot transport it with bushings. They need to be disassembled. Another example of this time surrounding area which can influence your measurement. This was measured on a transformer which was normally connected to GIS busbar. As such, it is not possible to test the transformer when it is connected because there is no access to terminals. The only thing you can do is actually to connect to the GIS bar through earth switch, which was located further away from the transformer, some hundreds of meters away. And this way, get access to the windings. And this is the response that we got in this condition. And our reference was for the same transformer made in part when it was not connected to the GIS, so we had direct access to the bushing terminals. So you can see quite big difference in certain region of frequencies where that busbar was included. A good thing in this case is that we have nice alignment of all three phases, so we could still treat this measurement as valid, but effect of busbar was clearly visible. Another mistake that can be made, or influencing factor that needs to be considered, is core earth. It can happen that transform is tested, that core and frame earthing is disconnected for purpose of insulation resistance measurement, and it can be either forgotten to be put back in place, or maybe made by another person from the team while another one is preparing for a SFRA test, and then the test is performed and traces do not match. So this is such an example where two traces were measured on the transformer with and without connected earth connection of the core and frame. When the transformer was tested again with that reinstated, then the new trace was as expected. Another factor, this one was the one which I tested myself. This was a transformer which was tested on site. Obviously, I pointed out two braids. These are two different phases. One braid looks like a braid, another braid looks like a braid. Their purpose is to make good connection of earthing points of different points of the housings, and they look perfectly normal. There is no visible difference between them, but apparently there was a difference. One was not correctly earthed, and this purple line here, this was my measurement which I did on one of the phases, where I connected my measurement lead to the terminal for the measurement, but that lead also have grounding connection. That grounding needs to be connected somewhere close to the bushing, to the good earth, and I apparently connected to that braid because it looked solid and proper, good for earthing, and I got this response much different than others. And I searched for the reason for that, and finally I found the reason. It was actually that earthing. So when I retested with my leads, test lead connected to different points, one of these three traces here is the same phase, but connected to ground in proper place. So these were influencing factors. As we know already what to look for when we test the transformer, and we know what can affect our traces when we measure them, we would like to use some reference if it is available. It's not always available, but when it is highly valuable because it can greatly increase confidence in our interpretation. By the way, I didn't say at the beginning, but I would like to tell you that if you have any questions, please write them in the question tab of your panel so that I can read them at the end. Okay, coming back to the reference results. Before we analyzed our traces on basis of comparison between phases. Unfortunately, this is not always the best way, because our traces can differ significantly without transformer being damaged. So there are two other options. We can either compare our traces with previous results, ideally made on this, basically made on the same transformer, ideally in the same location, the same condition. And for that, we need to know how it was tested before and what influencing factors could have affected these traces, so that we can follow up the same strategy. Or we might also have sister transformer, which has the same design, and we might be able to test it, or we already have test results for that one, so that we can compare with this one, because it is supposed to give you very similar test results. So that's why it is important to obtain the same test setup as was used for reference results. Here we have an example of reference taken from sister transformer. This transformer was tested in one of locations in Middle East. And when I tested it, I noticed some differences on the between the traces of low voltage side. This is not exactly this screen which is presented now. This is my second test which I did, but generally I had similar problems here. We had some disagreement between phases in this higher frequency range. So I came to the manager of the site and I said, okay, we are testing the transformer. In SFRA results, we have this problem that there are some differences. We are not 100% sure how to interpret them. Please, can you give us your any reference results if you have them? They said, no, we don't have. Okay, so please, can you allow us testing the sister transformer, which is standing next to this one? And they were reluctant because it was connected to the cable on high voltage side. So this connection from the cable is multiple hours, long duration job, and they didn't want to do it. Then I said, okay, maybe we can not disconnect high voltage side, we can just unearth it on the other side of the cable, as long as it's proven it's not inducing any voltage. So we did that. They disconnected the cable, they measured potential on the terminals, everything was safe. And then I did the same on the transformer, which was previously tested by me. And what I did, actually, that one was disconnected from high voltage cable. I reconnected it to that high voltage cable by shorting leads and measured that low voltage side again. And this is what I'm presenting here. There were still differences on in high frequency side, but this time as tested on LV side with cable connected to high voltage winding. So this was additional influencing factor which I introduced to my test in order to be able to compare it with transformer which I use for reference. And this is a reference which I obtained on the other transformer. So you can see, although not exactly the same, there were different cables connected to high voltage side. But again, in this region, we had similar response. So we understood this was a genuine feature of this design to have some differences in this region. Another transformer, another situation like that. Here we had a small distribution transformer with very good responses on low voltage side, but with some relatively high differences of only one trace on high voltage side. And again, we had a possibility to measure sister transformer, was standing next to it. This time it was scheduled for testing, so we tested it. And this was the reference. So after measuring the reference transformer, we understood again that this is a genuine feature of this particular design. So conclusion is maybe not making us very happy, but we need to remember that this is not always that good transformer has good responses or good looking responses. We need to understand there can be different cases. Okay, now I would like to present you several examples of successful SFRA measurement on deformed transformers. And so I will start from the easiest one. This is just one test made on the transformer, big 750 MVA auto transformer. It failed in service, and traces for 3 phases look like here. I didn't say before, there is a technique called short circuit test. This is made by doing the same tests, but with other windings shorted. If you do it that way, these traces will look like this trace here. But this was open test. The other winding was not shorted, and we were still getting a similar response. So the conclusion was easy. There was short circuits inside the winding. even though there was not outside the transformer, it was inside the winding. Transformer was damaged. We knew that from other sources as well, from DGA, from history of the events, so it was obvious. But it's quite often not that obvious. This is example of movement, of minor movement, just few turns moved, and transformer was potentially able to take a voltage and take a load, but fortunately we picked it up in time and it was not energized anymore. The transformer failed in service, it tripped, and a flashover marks across contacts of A phase of tap changer selector were found. So transformer was basically disconnected, oil was drained, tap changer selector compartments were open, and initially there was open circuit on phase A, and then there were some sparking marks on the selector. Everything was repaired, reinstated, so the transformer could be tested in condition without oil. And then we started testing. We did first sweep of frequency response test, and we saw almost, let's say, good response. All three match each other with some relatively good accuracy, but here are some differences, and especially in red phase is more different than any other of these two traces. Here, a little bit also here, a little bit here. We said, okay, let's try different tests. This was high voltage tap 1, so we did it at tap 19 without the regulating winding. So we have A phase visible here as well. This was visible here, and again in some other points, again outstanding slightly from the two other phases. Is it enough to say transformer is deformed? I don't think many people would be that brave to say it's not fit for service, but we had some more options to explore. We tested regulating winding on its own, and here the difference was more obvious. How we did regulating winding only? We did that through the tap changer selector contacts, because they were still open. We had access to them. So we measured regulating winding, and here the differences are more obvious. Again, phase A. That is in coincidence with previous findings where flashover on phase A was found and open circuits in that phase. And we also did interwinding tests, which is kind of ratio tests made with SFRA instrument. You can read about it in one of these documents from SIGRE, which I mentioned before. But again, phase A was different. So we started investigating further. Transformer was still drained from oil. There were a few hatches available, including that one of selector. And what we saw was actually here, originally there was a bracket holding tap leads entering the windings. And this bracket was broken in this part here. There should be continuity of this bracket, and one part is missing. So we said, okay, there is already some mechanical damage inside. There is a high probability there is really something inside. So the customer decided to scrap this transformer, and we participated forensic investigation. So during forensic investigation, we saw some tap leads deformed in this transformer. That bracket was further away here, so the leads actually broke that bracket, and this was the condition of the transformer. So it wouldn't be identifiable by any other test than this SFRA test that we did, and even that was not straightforward to interpret. But fortunately, we got to the bottom of this. Another example, that is coaxial collapse of the winding. So we had 400 kV, 240 MV auto transformer located in Great Britain. It was 35 years old, and it presented a backwards alarm in 2001. Transformer was switched out for investigation. Analysis of backwards gas and main tank oil indicated a serious fault, so we knew something happened inside. No abnormal system events were noted apart from that, and transformer was operating at 80% of loading during at the moment when it failed. We did electrical tests on this transformer. There was hardly nothing conclusive from all the electrical tests. The only thing which we saw was this. These are 3 phases measured across, I think it was common winding. In this case, it is presented in linear scale. You can see the bottom scale is no longer logarithmic, it's linear. So we don't see very well what's happening in lower frequencies, but we see much better what is happening in highest frequency range. And if we use logarithmic scale, all the features visible here, they will be just in the corner somewhere. So this scale was apparently the good choice. And what we saw here was little difference between blue phase or blue line representing A phase and another 2 phases. If you look carefully, it outstands the other 2 phases more than the other 2 between each other. Is it enough to tell something is bad with these results? Well, for this one, we had reference from past. This test was made in 2001 after the failure, after the backwards alarm, and before in 1994, the traces look like this. So if you look carefully, okay, this is before, after, before, before, and after. So, sorry, this is before, that one was after. So basically the after results show this slight shift of the coil, of the traces, and that gave us hint that something is going wrong with A phase of this transformer. So this was the previous result, and this was another transformer with which we already had experience before. Again, in 1994, sister transformer failed, and again it failed in similar ways. So there was again this A phase shifted, but to higher degree. So we had some supporting information, and this is what we found. And so the coil was crushed from top and from bottom. So you can see the bottom blocking system is damaged, and top supports were also damaged, and it's also visible on the leads. They collapsed, and the winding was a little bit twisted. So this was identified with SFRA. Another example, large buckling deformation. In this case, we had 750 MVA transformer, again auto transformer, 400 kV to 275 with tertiary winding. There were no taps in this one. It was built in 1966, and deterioration in DG results was observed over the years. It was removed from service for investigation. So this was the DGA. If you look more carefully, you will see there were at least 2 events. This is acetylene and ethylene only, and here before we have all other gases, including hydrogen, which was raising. So this was a driver for the customer to decide it will be tested. So as we look closer at ethylene and acetylene, we can see at least 2 events in which it rapidly rose and then it was decreasing and rose again, decreasing. There was something similar in past as well, to much lower extents. One of these events coincided with CT failure somewhere in the system. So the transformer was subject for testing, And power factor tests show that B phase measured between main windings and tertiary showed much lower capacitance than the one of sister transformer, and much higher power factor test than the one of sister transformer. And at the same time, tertiary winding capacitance to ground was higher than that one of sister transformer. So we had quite strong indication that something is wrong here. And we also had SFRA results, which showed us this. And this is 2000, when reference results came from. And this is 2005, when we tested it, when it was decided it will be subject for investigation. If you look carefully, you will see that B phase here differs from other traces much more than here. Here is actually quite good, up to some area above 1 megahertz, when traces normally naturally start and deviate slightly. In this case, middle phase trace differed from the previous one strongly. And this is what was found. Initial view was that top clamping platform was broken off on B phase winding, and when it was disassembled and scrapped, this is how the winding inside looked like. So there's severe buckling deformation in this transformer, and we could see it in our traces. And here, last example. In this case, we identified tap winding movements. So this was 275 down to 33 kV, 120 MVA transformer feeding steelworks, and it suffered flashover between taps while being kept on hot standby. It was opened, and barrier board between tap changer and main tank was found broken. SFRA tests indicated movement of tap winding. And so here, little comment about that. It was found on tap 1 where all taps were in, but not on tap 10, which was the nominal tap position, or actually middle tap position, with all the regulating winding out of circuit. So this test, as proposed in IEC standard, now this is one of tests to do it with all taps in and all taps out. This test helps us identify the problem is located inside the regulating winding. We had reference responses from sister transformer. The only problem was that the faulty transformer was without oil, while the reference was oil filled. So this is what we had. This is our measurements on tap 10, which means without any tap winding included. This is measured on the faulty transformer, and this is our reference transformer, sister transformer of the same design. Then this is measured on tap 1 where regulating windings included in the measurements. And we can see the C phase much different than the other two. And this is our reference on tap 1. There is no such an effect like here. So we saw the C phase was really the one which was affected. And this is what we found. As I saw before, this broken barrier board. We have some deformations here of the leads connecting the winding through the barrier board to the tap changer, and some flashover marks on the C phase. Here we can see them better. And this is what was found in the winding. So this is our regulating winding with some flipped leads as seen on this picture. So these are all my case studies which I presented, and I have some conclusions to this presentation which I just gave. The first conclusion is that reference results, if they are available, can greatly support interpretation of results. So you could, if you have the reference results, you should do everything you can to adapt your testing in such a way that reference results can be used. So the same tap position, the same condition of a transformer, if something was described in previous reports, please apply the settings, the setup, maybe open or closed delta winding. If you cannot get a good comparison with reference results, try to identify difference. Maybe this is one of influencing factors, and just by changing something in your test, you can match the reference results and tell, okay, transformer is in good condition. Otherwise, you will have to tell something about this measurement, and it's not gonna be that easy. It is also important to be aware of a number of different factors which can affect the measurement, like tap position, state of stabilization, winding. So results obtained in different conditions may not make a good reference. This is what I just said at the equation of the first conclusion. And the last one, which is maybe a little disappointing, but that's the life, we need to accept it, is that little difference between your traces can still mean a dangerous deformation, like we saw on some of the cases. But at the same time, large differences can be attributed to factors, these influencing factors that can affect the measurement. So you need to come open-minded to the test, to the transformer, and think carefully what that actually means, what you are observing when you make a test. So that was my presentation, and thank you very much for listening. And I will see if there is anything in questions. Apparently, no, I don't see any questions raised during my presentation. So thank you for attendance. There is a document, this presentation, which I just presented in handouts. Okay, there is one question. Let me read it. Should we test all test taps? Well, I always say that the more tests you do, the better, or more often you test transformer, the better, because it brings you some more information. And then you can bring something from that, but testing all taps is, in my opinion, way over the top. If you follow IC standard, it tells you tap position which with all the taps, with all the turns of regulating winding included, and tap position with the regulating winding excluded from the taps, from the test. So this is also my recommendation. It actually came from Doble, that recommendation. Don't see how I can easily read this. Maybe I can expand the window. So in general, I don't recommend tests this on all tap positions, but with and without regulating winding, yes, I recommend. Okay, now I have to carefully read the rest of it. But it's not that easy to read. Since SFRA is considered to be fingerprint of the transfer, will the result vary if I were to use an equipment from different OEM for SFRA once it's in service? Okay, so if you use different equipment, theoretically it shouldn't matter. We did comparison within SIGRE in past, where we compared different instruments in past. So it came to our mind that different types of, or different impedance level of the measurements, that means there was mainly either 50 or 75 ohm impedance used in an instrument, made the traces different. But as far as I know, every manufacturer adapted to 50 ohm, and this is no longer a problem. So theoretically they shouldn't, but to be on a safe side, I see many buyers, many customers, they still insist to use the same instrument in a factory that they use on sites. So I don't think everybody trusts this will be exactly the same. Let me just check one thing. I got a hint how to read them easily. Hold on.
Rafal?
Yes.
You can click in question section, the square in the right side, and then the questions
Then it pops up, yes?
Yes.
This one. Okay, I will try it now. In
Thanks.
questions section, okay. Okay, it's still small, but it's separate now. Okay, now I see much more questions, okay. So you don't let me go out quickly. Okay, now I see them better. Thank you. Okay. Hi, my query is pertaining to identifying the defect in the transformer. How much difference in dB value indicates defects for each frequency range and supposedly type of fault inside the transformer? Okay, so this is a question which I actually answered in my conclusions. I'm afraid that dB value cannot be quoted, even if in the latest brochure from SFRA, you can see there is no such dB value and no guidance on that, because some deformations are very delicately indicated by traces, and I'm afraid it's not gonna be that easy that you just run it and that's it. In the latest document which I described at the beginning, that one from SFRA, brochure analyzes different different numerical indices that were used by researchers worldwide, and we try to assess them. So you can read carefully that document and look at these indices. There is more than 20, I remember, of them, and they are categorized how well they react to different types of faults. On basis of the library that we constructed within the SFRA. So answer is not that easy. I would recommend you read that document and see how complex that is. Okay, picture with effect of insulation liquid. Green line has 2 drops on magnetic core frequency range, and red has only 1. Indicating that probably different phases has been compared, right or wrong? Picture with effect of insulation liquid. Let me find it. This one? Yes, you're right. You might be potentially right, because it was not made by me, this measurement. So I don't know exactly, okay? It could be potentially that the red one is from B phase, but it sometimes also happens that the 2 dips, which are typical for outer limb, they join together in some magnetical condition of the core as well. So it is possible what you just pointed out, that they are not from the same trace, but the main idea is still the same. There is a shift between them. And whether this was exactly the same or not, I should dig out previous presentations to see who actually did this test and check that out. I believe it would be the same phase if someone connected these two traces together. Well, thank you for spotting this out. The left picture is touching the construction. Left one picture is touching the construction. I don't know what that means. Sorry. I don't know which slide and which picture. So if Mr. Laskov could explain more in second question, I will come back to that. Okay, when testing on an electrical substation due to induction of neighbor electrical lines, sometimes the curves are wrong compared to previous tests. Even the magnetization in the magnetic circuit doesn't allow the curves to be identical. What can I do to make the curves right on the field when the neighbor electrical lines can be turned off? Well, so basically this I would expect to show you some influence on your trace around 50 Hertz area. And if you know such influence is valid there and you cannot obviously switch off the line and your leads are still picking up they're inducing some currents, the best thing you can do is to understand that 50 Hertz and around there will be usually some noise visible. They are affected by this phenomenon. This has nothing to do with winding deformation. If there was a winding deformation, it would progress further through frequencies. So that would be the case. Okay, so next one. There are some invitations, so welcome to me. I understand there is nothing below that because I cannot expand that. This looks like hello and good day. Okay, should the SFRA test fail, should the SFRA test fail, what are other tests you can perform to prove that the failed test result is true? Can the ratio and DC winding resistance test help as for further analysis? Well, that depends on the case. So if this is severe damage in the transformer, like everything mashed inside, surely ratio test would show this, or magnetizing current quite often shows you that something wrong is inside, and the SFRA will also show it. In cases like some of the ones which I presented today, it is not that easy to find another test which will support your findings from SFRA. So this is always case by case situation. Basically, if you have doubts, what I recommend, dig deeply into the bottom, whatever you can do. You have several different test techniques like winding resistance ratio or power factor test. Please use them anyway, because even if they don't show you anything, if you have doubts, last thing you want is to write in your report, oh, I saw something, but I don't know what that means. So yes, you should investigate further whether it will be identifiable through other tests or not. That's a question of nature of that problem. Okay, next one. SFRA method used for generator turbine rotor winding condition assessment, especially for turn-to-turn fault, possible or not? No, I didn't try, sorry. I am not a generator guy. I don't test them. I never tried. I cannot tell you that. Is it necessary to do the SFRA under routine tests on a transformer? Yes, of course. This is question of your procedures, of your policy, how you want to test your transformers. And as I said before, the more tests you have, the easier it is later in future to pick up something from past. At least SFRA should be done, in my opinion, once in a lifetime after the last installation, so that you have good reference for your future test. If it's moved to another place, I would suggest do it again, especially that you will test this transform anyway, and there is someone needed to test the transform, so why not include SFRA? Whether in routine tests, that's a question of your time and money you want to spend. I would suggest to do it. It's not that long test. And if you already have instrument available, why not? It is also sort of routine tests, so you might pick up a problem in a transformer even if it didn't fail by other indications. So you could possibly see something from them. So yes, I would recommend. Can you perform SFRA on a offload tap changer? Well, not on the tap changer, but on transformer with offload tap changer, yes, of course. There's no difference whether it's on-load or offload. The idea is still the same. You test the windings and you measure it as per your routine test plan. Is it recommended to the SFRA where the transformer, I think, is half of oil? You saw on the picture before that oil affects the results. If it's half of oil, it will be half distorted trace. So it is not recommended to do it this way, but sometimes you have no choice. Transformer is drained from oil for some reason, maybe after some internal review, and you can either test it or not test it. So it's always better to test it in conditions that you have and then try to interpret it. In the case study of the actual collapse, what instruments were used for both tests, especially in 1994? Okay, so this is a question to my colleague. It was not tested by me, but in 1994, I believe it was tested with HP analyzer. So SFRA tests in Great Britain was actually made before the first instrument was produced. And the first instrument, I believe, was produced by Doble and was called M5100. Outdated today construction, but it was still, the measurements are still valid. And before that, the technique was performed with Hewlett-Packard analyzers. So the traces were made in more complicated way, more engineering knowledge was needed to do the test, but this is how it was tested at that time. In 2001, I don't remember whether the first instrument was already available. If not, maybe again, HP analyzer. Can you perform a SFRA test when the transformer is half filled with oil? That was already answered. When shorting the windings, whenever doing the trace, do you have to ground the windings as well or short the windings together only? Well, we normally short them only, but that is always important to write in your report what you actually did, because in the end you need to present your results. You have to interpret them. I think they will be equally interpretable whether it's short and grounded or not. So it's up to you how you do it, but it's important that you follow the same procedure when you test them next time. So please write in your report what you did, how you tested them, because someone in future can short them and not ground, and they will be in trouble. So they should know that. From interpretation point of view, I don't see that will affect your interpretation easily or greatly. Okay, there will be traces will be different, but different for all three phases. How can FSRL testing give also more information regarding the cases shown in your presentation? I don't know. I don't use these methods. but I understand that FRSL method is dedicated to shorted short circuit between parallelly running conductors inside the winding. So when there is such a short in the damage, it will be possibly also visible through that technique. If that's the case, you saw some of my examples where there was some winding deformation without breakdown of continuity of the leads of the cables in the windings of the conductors. So in this case, FRSL might not help, but that's the same problem as with all other techniques. Some problems can be visible through one technique and not through another, and this is exactly the same. Should we test all test tabs? All tabs. Okay, that one I saw before in my previous view. I don't recommend all tabs. I recommend all regulating in and without regulating winding. Okay. Usually we perform the UCC percent and FRSL first before the SFRA. You mean short circuit impedance and FRSL before SFRA. Okay, SFRA is sensitive to core magnetization. And so I recommend that you do it before any test that magnetizes the core. And that's it. If you need to do other tests that magnetize the core before SFRA, then I recommend to use one of instruments that are available in the market that can demagnetize the core. Although I would prefer to do SFRA first anyway. What should we do if I don't have, where is it? If I don't have any reference of transformer response? So that would be more difficult interpretation then. It's all okay when you have all three phases aligning nicely each other. So this is what you normally can do anyway. I can't imagine a situation in which you only have one phase available. So you can compare three phases between each other. But when they don't align very well, you can try to interpret them on basis of these influencing factors, which I presented before, to see whether one of them could be reason for what you are seeing, or if it's similar to something what you saw before on another transformer of similar type maybe. So yes, it's gonna be more difficult then, and it's a majority of the cases. But if you have a network of transformers, there are usually more transformers of similar type, and you can also schedule another transformer for testing, which would be similar. Which transformer can't be measured with SFRA method? I'm meaning the transformer for some special usage like starting for gas turbine. Well, any transformer will be measurable. If there is a winding inside, you will be able to measure it. The main thing is that the less complicated windings, the less complicated the trace is. So if you have a small transformer with low voltage winding operating, let's say at 600 volts, and this is foil winding, just few turns, your response will be more and more flat, and it will not show you too many details, that response. So the less complicated winding, let's say, the less details you can see, and you will see just less from the test. Okay, next one. I noticed that you often change the frequency scale to linear. Interesting approach to analyze the higher frequency responses. Yes, actually, this is one of the ways one of my colleagues quite often looks at the traces. We also look, this is quite easy to click and have it in linear scale, but especially in past, it was quite popular to look at them in linear scale. And then what we did is we normally had that in linear scale and then divided to sub areas of that frequency range, so that we could still zoom into lower frequencies anyway. But my preference is to look at logarithmic scale. It's what I'm used to more. And then I once click to see this at linear scale to see if there's something what draws my attention as well. But yes, you can zoom in, zoom out, you can do whatever you want in order to look at the traces. I noticed that you often, that's the same. What is the best method to analyze SFRA tests if we don't have previous results? I already said that. Hold on, excuse me. We got some message. Okay, a suggestion that we ran out of time. Well, there are just few more questions missing, so I would continue. When doing commissioning tests on a newly installed transformer, is it okay to just test extreme raise, nominal, and lower tap? I think yes. I wouldn't, as I said before, I wouldn't go through all tap positions. All AG or LV phases must have the same trace. Okay, between phases, I already presented, it doesn't have to have the same response depending on the design of the transformer. So it doesn't have to be the same, and when it is not the same, it is good to have reference results for comparison. Slide 23 left, picture grounding is touching the metal constant. Aha, okay, now I know what you mean. This. Okay, it is okay, one is touching, one is not touching, but that was not the case. This is not what I wanted to say. My point was that one of these braids was not well grounded anyway. Even if it's touching, the painted metal will still work, doesn't matter. It didn't provide me good earthing points, so the trace was not correct. Okay, A, B, C, AG phases must have the same trace, or why they are not exactly the same? As I said before, it is nice when they are aligned very well between phases. It is not always the case because design doesn't always allow it. So when they are exactly the same, you can feel happy that your measurement is positive. There is nothing wrong. If they don't align very well, interpretation needs to be expanded, maybe on basis of reference results, on basis of your previous experience to see what could have gone wrong, maybe on basis of history of the transformer, and maybe the transformer failed in service and you arrive for this reason. So if they don't align each other perfectly, it can mean both. And usually low frequency side differs in a way that outer traces have 2 dips in the trace, and middle phase has only 1. Okay, next question. The slide has a question. Can you spot it? Okay, that was the same question. I went to use the Chinese standards. I don't know content of the standards. It was developed well before the latest SFRA document, and it was not considered as a good reference of everything. So I'm not sure if it's okay. I cannot tell too much about it, but I don't see it to be followed very strongly. Can we perform SFRA on generator? I already answered, I don't know. it will present you some information, but I don't know how to interpret that. Who's left? Hi, Jen, sorry I'm late, but they sent me a reminder that the webinar starts at 11:30. Okay. Someone sent email asking for presentation. The presentation is available in the panel, so please download. Why is it used dB? Is it important, the magnitudes? Well, we look at overall shape of the trace. Yes, it was once decided to use dB scale versus frequency scale, and this is how it is done. It could be done maybe in voltages, but then someone would have to define other parameters, how the voltages are obtained. So this is what was agreed a while ago, what was popularized, and this is how it is going on. So this is also what was implemented in instruments, and this is how we do it. Okay, that was the last question. So thank you very much for the questions. Thank you for attendance. I hope you enjoyed, and I hope it was informative for you. And I wish you a good day. Thank you very much. Jessica, could you close down the meeting?
Yes, sure.
Thank you.
Thanks. Goodbye.